Imagine flipping a switch and suddenly accelerating to the speed of light. In that instant, you might not just be breaking the ultimate cosmic speed limit, you could be triggering a catastrophe that unravels the very fabric of reality itself. The equations that govern our universe suggest that reaching light speed doesn't just bend the rules of physics, it could shatter them entirely, potentially creating paradoxes that cascade through space and time like cosmic dominoes. Today, we're diving into one of physics' most terrifying possibilities. Why traveling at the speed of light might not just be impossible, but could literally destroy everything we know and love about our universe. If you're fascinated by the mind-bending extremes of physics and want to explore more cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. And here's something I'd love to know. If you could break one law of physics without consequences, which would it be? And what would you do first? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. To understand why light speed travel could be catastrophic, we need to grasp what happens to space, time, and matter as we approach this cosmic speed limit. Einstein's special relativity, confirmed by countless experiments from particle accelerators to GPS satellites, tells us that strange things happen as objects accelerate. Time dilates, lengths contract, and mass effectively increases. But these aren't just mathematical curiosities. They're fundamental features of how our universe maintains consistency and prevents paradoxes. Let's start with what physicists call the mass-energy equivalence problem. As you accelerate any object with mass toward the speed of light, its relativistic mass increases exponentially. At 90% the speed of light, an object's mass roughly doubles. At 99%, it's 7 times heavier. At 99.9%, it's 22 times heavier. The closer you get to light speed, the more dramatic this increase becomes, approaching infinity as you near the ultimate barrier. This isn't just about needing more fuel. If you could somehow reach exactly light speed, your mass would become infinite. Infinite mass means infinite energy, and infinite energy concentrated in a finite space has a name in physics: a black hole. But not just any black hole, we're talking about a black hole with infinite mass, something our equations can't even properly describe. The mathematics literally break down, producing what physicists call a singularity, a point where the known laws of physics cease to function. The Large Hadron Collider at CERN accelerates protons to 99.99999% the speed of light. At these velocities, each proton carries the kinetic energy of a flying mosquito, impressive for a subatomic particle. But that last tiny fraction toward true light speed would require more energy than exists in the entire observable universe. Nature seems to have built an exponentially rising wall that prevents anything with mass from reaching this ultimate velocity. But let's imagine, just for the sake of argument, that we found some exotic loophole, maybe negative mass, extra dimensions, or some undiscovered physics. What would happen if we actually accelerated a spacecraft to light speed? This is where things get genuinely terrifying. The moment you hit light speed, time dilation becomes infinite. From your perspective aboard the ship, time would stop completely. You wouldn't experience the journey. You'd arrive at your destination the instant you departed, no matter how far away it was. This creates our first universe-breaking paradox. If no time passes for you during the journey, how can you decelerate? How can you even make decisions or have thoughts? Your brain, your computers, every physical process would be frozen in time. You'd be trapped in an eternal instant, unable to slow down, unable to change course, unable to exist in any meaningful way. It's not just impractical, it's logically impossible. The paradoxes get worse when we consider causality, the fundamental principle that causes must precede effects. Special relativity shows us that simultaneity is relative. Events that appear simultaneous to one observer might occur at different times for another observer moving at a different velocity. As you approach light speed, this effect becomes extreme. At light speed itself, the order of cause and effect breaks down completely. Imagine you're traveling at light speed from Earth to Alpha Centauri, about 4.3 light-years away. From Earth's perspective, your journey takes 4.3 years, but from your perspective, with infinite time dilation, you arrive instantly. Now here's where it gets weird. From certain reference frames, you would arrive at Alpha Centauri before you left Earth. Effect would precede cause. You could theoretically send a message back to Earth that arrives before you departed, creating a causal loop that physics can't resolve. These aren't just thought experiments. Tachyons, hypothetical particles that always travel faster than light, would necessarily travel backward in time from certain reference frames. If such particles existed and could carry information, you could send messages to your own past, creating grandfather paradoxes where you could prevent your own existence. The universe seems to protect itself from such paradoxes by making faster-than-light travel impossible. The cosmic speed limit isn't arbitrary, it's woven into the geometry of spacetime itself. In 1905, Einstein showed that space and time aren't separate entities, but parts of a unified spacetime. The speed of light is the conversion factor between space and time, like the exchange rate between currencies. Trying to exceed light speed is like trying to travel north from the North Pole. It's not just difficult, it's meaningless within the structure of reality. But the dangers of light speed travel go beyond paradoxes and impossibilities. Let's consider what would happen to the vacuum of space itself. Quantum field theory tells us that empty space isn't really empty. It seethes with virtual particles, constantly popping into existence and annihilating. This quantum foam, as physicists call it, has real, measurable effects like the Casimir force between closely spaced plates. As you accelerate toward light speed, these quantum fluctuations would become increasingly violent from your perspective. The vacuum itself would appear to heat up, a phenomenon related to the Unruh effect, where accelerating observers perceive empty space as filled with warm radiation. At speeds approaching light, this radiation would become intense enough to incinerate any material object. But at exactly light speed, something even more catastrophic might occur. The quantum vacuum could destabilize entirely. Speaking of the mysteries of light speed and what might exceed it, if you're curious about whether anything in the universe actually can break this cosmic speed limit, check out my video, Can Anything Travel Faster Than the Speed of Light?, where I explore the loopholes and phenomena that seem to violate Einstein's rules. The link is in the description below. Now back to why reaching light speed could unravel reality itself. The vacuum catastrophe in cosmology shows us that we don't fully understand the energy content of empty space. Quantum field theory predicts that the vacuum should have an enormous energy density, 10 to the power of 120 times larger than what we observe. This discrepancy, the worst prediction in the history of physics, suggests something fundamental is missing from our understanding. If traveling at light speed disrupts whatever mechanism keeps vacuum energy in check, it could trigger a phase transition in the vacuum itself. Think of it like supercooled water that remains liquid below its freezing point. A tiny disturbance can trigger instant crystallization throughout the entire volume. Similarly, the vacuum of space might be metastable, stable for now, but capable of transitioning to a lower energy state if sufficiently disturbed. A massive object reaching light speed could be that disturbance, nucleating a bubble of true vacuum that expands outward at the speed of light, destroying everything in its path. This isn't science fiction, it's a genuine concern among theoretical physicists. The Higgs field, which gives particles their mass, might not be in its lowest possible energy state. If it's metastable, a sufficiently energetic event could knock it into a lower state, fundamentally changing the laws of physics within the expanding bubble. Atoms would no longer be stable. Chemistry would cease to exist, life as we know it would be impossible, and the bubble would expand forever, eventually consuming the entire universe. The discovery of the Higgs boson at the Large Hadron Collider in 2012 actually made this scenario more plausible. The measured mass of the Higgs suggests our universe might indeed be metastable, balanced on a knife's edge between stability and catastrophe. While natural processes are unlikely to trigger vacuum decay for trillions of years, attempting to accelerate macroscopic objects to light speed might provide exactly the kind of extreme conditions needed to tip the balance. Let's examine another universe-ending scenario, the creation of microscopic black holes. As mass approaches infinity at light speed, gravitational effects become extreme. The concentration of infinite mass energy in a finite region of space would inevitably collapse into a black hole. But this wouldn't be a normal black hole with finite mass that eventually evaporates through Hawking radiation. It would be a singularity with infinite mass, growing without bound, consuming everything around it. The gravitational waves from such an event would be catastrophic. LIGO and Virgo have detected gravitational waves from colliding black holes with masses dozens of times our Sun. These events shake the fabric of space-time itself, stretching and compressing distances across the universe. An infinite mass black hole would produce infinite gravitational waves, potentially tearing space-time apart like ripping a piece of fabric. The very structure that allows objects to exist and move through space could be destroyed. Even more terrifying is what happens to information at light speed. The holographic principle in physics suggests that all the information in a volume of space is encoded on its boundary, like a hologram. As you approach light speed, length contraction reduces distances in your direction of travel. At exactly light speed, the entire universe would be compressed to zero thickness from your perspective. All the information in the universe would need to be encoded on a two-dimensional surface with zero area, an impossibility that could cause information itself to be destroyed. Information loss is one of the deepest problems in physics. Stephen Hawking's black hole information paradox asks what happens to information that falls into a black hole. After decades of debate, most physicists believe information must be preserved somehow, but light-speed travel could create a situation where information has nowhere to go, no way to be encoded. The universe might respond to this impossibility by preventing light-speed travel at all costs, or by unraveling if the barrier is somehow breached. The chronology protection conjecture proposed by Hawking suggests that the laws of physics conspire to prevent time travel paradoxes. Whenever a situation might allow backward time travel, quantum effects build up to make it impossible. Light-speed travel, with its infinite time dilation and causality violations, would trigger these protective mechanisms. But what if we overwhelmed them? The universe's defense mechanisms themselves might become the source of catastrophe. Consider what particle physicists call the firewall paradox. At the event horizon of a black hole, quantum effects might create a wall of high-energy particles that incinerates anything trying to cross. Something similar might happen as objects approach light speed. The vacuum fluctuations, time dilation effects, and quantum corrections could create an impenetrable barrier of infinite energy. Trying to push through this barrier might release that energy catastrophically. The cosmic censorship hypothesis proposes that singularities, points where physics breaks down, are always hidden behind event horizons where they can't affect the outside universe. But a light-speed traveler would be a naked singularity, a breakdown of physics exposed to the universe at large. The cosmic censorship mechanism itself might cause a catastrophic response, perhaps creating an event horizon that expands to engulf everything, turning the entire universe into the interior of a black hole. Recent observations from the Event Horizon Telescope, which imaged black holes in M87 and our galactic center, show how extreme gravity warps spacetime around singularities. The glowing accretion disks we see are matter spiraling toward points of infinite density. A spacecraft reaching light speed would create similar distortions, but without the protective event horizon. The naked warping of spacetime could propagate outward, destabilizing the geometry of space itself. The mathematics of general relativity becomes even more troubling when we consider rotating objects approaching light speed. The Kerr metric describes rotating black holes, where spin creates additional spacetime distortions. A spinning spacecraft accelerating toward light speed wouldn't just face infinite mass, it would generate infinite frame-dragging effects, literally twisting spacetime around it like a cosmic tornado. This rotational energy, becoming infinite at light speed, could tear holes in the fabric of spacetime itself. Physicists at the Laser Interferometer Gravitational Wave Observatory have measured how rotating massive objects create gravitational waves that carry away energy and angular momentum. But an object spinning at light speed would produce gravitational waves of infinite amplitude. These wouldn't just ripple through spacetime, they would be cosmic tsunamis, potentially shredding the dimensional structure that allows our universe to exist in 3 spatial dimensions plus time. Let's dive deeper into the quantum mechanical catastrophes. The uncertainty principle tells us we can't simultaneously know a particle's exact position and momentum. As objects approach light speed, their momentum approaches infinity, which means their position becomes infinitely uncertain. A light-speed spacecraft wouldn't just be in one place, it would be everywhere along its trajectory simultaneously, existing in a quantum superposition across potentially infinite distances. This isn't just weird, it's universe-breaking. The spacecraft's infinite superposition would interact with every particle along its path simultaneously. The resulting quantum entanglement would be infinite and instantaneous, connecting every point in space. This could collapse the wave function of the entire universe, forcing every quantum system to decohere simultaneously. Reality itself might crystallize into a single, frozen state, ending all change and motion forever. The Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state, would face an impossible challenge. A light-speed object with infinite momentum would need to exclude every other particle from its quantum state across the entire universe simultaneously. This could trigger a cascade of quantum state changes, forcing every electron, proton, and neutron in existence to reconfigure instantaneously. Matter as we know it could simply cease to exist. Consider what we've learned from cosmic ray physics. The oh my god particle, detected in 1991, was a proton traveling at 99.999999999999999% of light speed. It carried the kinetic energy of a baseball thrown at 60 miles per hour, all in a single subatomic particle. When it hit Earth's atmosphere, it created a cascade of secondary particles covering several square kilometers. Now imagine not a single proton, but an entire spacecraft reaching true light speed with infinite energy. The collision between such an object and even a single atom of interstellar hydrogen would release infinite energy. This wouldn't just destroy the spacecraft, it would create an ever-expanding sphere of destruction. The energy release would be sufficient to create particle-antiparticle pairs from the vacuum, which would annihilate and create more energy, feeding a runaway reaction that could consume all matter and energy in its path. String theory, our best candidate for quantum gravity, suggests additional complications. In string theory, particles are vibrating strings in 10 or 11 dimensions, with extra dimensions compactified at subatomic scales. The infinite energy of light-speed travel could pump energy into these extra dimensions, potentially decompactifying them. Suddenly, our familiar three-dimensional space could unfold into higher dimensions, fundamentally altering the nature of reality. The anthropic principle tells us we observe a universe compatible with our existence. The specific values of physical constants, the speed of light, Planck's constant, the gravitational constant, seem fine-tuned for complexity and life. Light-speed travel might disrupt this delicate balance. The infinite energies involved could shift these constants, even slightly, making atoms unstable, preventing chemistry, or causing the universe to either collapse or expand too rapidly for structures to form. Recent experiments at CERN and other particle accelerators have probed energies up to several TeV, tera-electron volts, recreating conditions from microseconds after the Big Bang. But the infinite energy of light-speed travel would dwarf these experiments by literally infinite factors. We'd be creating conditions that didn't exist even at the moment of cosmic birth, potentially triggering phase transitions in fundamental fields that could rewrite the laws of physics. The false vacuum hypothesis becomes particularly terrifying in this context. Our universe's vacuum might be like a ball perched on a hill, stable but not at the lowest possible energy. The infinite energy concentration of light-speed travel could kick it over the edge, triggering vacuum decay. A bubble of true vacuum would expand outward at light speed, inside which different physics would apply. Particles might have different masses or not exist at all. The bubble would be invisible until it hit you, offering no warning before annihilation. Quantum chromodynamics, the theory of the strong force, predicts that at extreme energies, quarks and gluons form a quark-gluon plasma. The relativistic heavy ion collider has created tiny droplets of this primordial soup, which existed microseconds after the Big Bang. Light-speed travel would create conditions far more extreme, potentially liberating all quarks from their confinement within protons and neutrons. Matter throughout the universe could dissolve into a sea of free quarks, ending atomic structure forever. The cosmic microwave background, that faint echo of the Big Bang discovered by Penzias and Wilson, would appear infinitely blue-shifted to a light-speed traveler. This gentle radiation, currently at about 2.7 Kelvin, would become a wall of infinite energy photons. The interaction between the traveler and this radiation would pump infinite energy into the quantum vacuum, potentially reigniting the conditions of the Big Bang itself, creating a new universe that overwrites our own. The implications for dark matter and dark energy are equally catastrophic. We know dark matter makes up about 27% of the universe's energy content, interacting only through gravity. But infinite gravitational fields from light-speed travel could force dark matter to interact in new ways. The invisible scaffolding that holds galaxies together might suddenly become violently reactive, collapsing or exploding in ways we can't predict with our limited understanding. Dark energy, that mysterious force accelerating cosmic expansion, presents an even greater danger. It makes up 68% of the universe's energy density, and we barely understand what it is. The infinite energy densities near a light-speed object could interfere with dark energy's negative pressure, potentially reversing cosmic acceleration. The universe might suddenly begin contracting, heading toward a big crunch where all matter and energy converge into a singular point, ending space and time as we know them. Let's examine what the James Webb Space Telescope has revealed about the early universe. We've observed galaxies from just a few 100 million years after the Big Bang, when the universe was much denser and hotter. The conditions around a light-speed object would be even more extreme than those primordial environments. We'd essentially be creating a localized region with energy densities exceeding the early universe, potentially triggering the same kind of rapid inflation that expanded the cosmos in its first fraction of a second. But this new inflation wouldn't be controlled or uniform. It would be chaotic, creating bubbles of rapidly expanding space that tear apart existing structures. Galaxies, stars, planets, even atoms would be ripped apart by exponentially expanding space. The orderly cosmic web we observe, with its filaments of galaxies and vast voids, would be replaced by a chaotic foam of disconnected regions, each expanding too fast for light to travel between them. The holographic principle, supported by theoretical work on black hole entropy, suggests our three-dimensional reality might be encoded on a two-dimensional surface. Light-speed travel could overload this encoding. Imagine trying to compress infinite information onto a finite surface. The hologram would break down, potentially causing three-dimensional space to collapse into 2 dimensions or fewer. Reality might literally become flatter, making complex structures like atoms and molecules impossible. Observations from gravitational wave detectors have shown us how massive accelerating objects create ripples in spacetime. The LIGO and Virgo collaborations have detected dozens of black hole mergers, each one briefly releasing more power in gravitational waves than all the stars in the observable universe combined. A light-speed object would produce gravitational waves of infinite amplitude, not just rippling space-time but potentially tearing it apart like tissue paper. The Pioneer and Voyager spacecraft, humanity's most distant emissaries, have taught us about the interstellar medium. Space isn't empty. It contains about 1 atom per cubic centimeter, plus dust, cosmic rays, and magnetic fields. At light speed, each of these particles would hit with infinite energy. The spacecraft wouldn't just be destroyed. Each collision would create cascading particle showers that propagate outward, turning the entire galaxy into a particle accelerator of infinite energy. Quantum entanglement, what Einstein called spooky action at a distance, would face paradoxes at light speed. The EPR paradox shows that entangled particles maintain instantaneous correlations regardless of distance. A light-speed object would exist everywhere along its path simultaneously due to infinite length contraction, potentially becoming entangled with every particle in the universe. This infinite entanglement could cause all quantum systems to collapse into a single, universe-spanning wave function. The cosmic censorship hypothesis proposed by Roger Penrose suggests nature abhors naked singularities, points where physics breaks down that aren't hidden behind event horizons. Light-speed travel would create exactly such a naked singularity, exposing the universe to undefined physics. The mechanism that enforces cosmic censorship might respond by creating an event horizon that expands to engulf the entire observable universe, effectively ending reality as we know it. Recent studies of fast radio bursts, mysterious millisecond pulses from distant galaxies, show how extreme events can be detected across cosmic distances. A light-speed catastrophe would produce signals unlike anything we've observed. The burst of radiation, gravitational waves, and exotic particles would propagate outward at light speed, giving no warning before annihilation. Civilizations across the universe would see a wall of destruction approaching, powerless to escape. The many worlds interpretation of quantum mechanics suggests every quantum event branches the universe. Light-speed travel with its infinite quantum effects might cause infinite branching, creating uncountably many universes simultaneously. The computational resources required to sustain such infinite branching could exceed what's possible even in principle, causing a breakdown in the quantum mechanical framework that allows reality to function. Cosmic inflation theory explains why our universe is so uniform on large scales. During inflation, space expanded faster than light, but this was expansion of space itself, not motion. through space. Light speed travel through space is fundamentally different and could trigger a new type of inflation where space doesn't just expand but tears apart. The smooth, homogeneous universe we observe would be replaced by a fractured reality where different regions obey different physics. The measurement problem in quantum mechanics, how quantum possibilities become classical realities, would face its ultimate test. A light-speed object would exist in an infinite superposition of states. Any attempt to measure or observe it would require collapsing an infinite wave function, potentially freezing the entire universe into a single quantum state. Change, motion, and time itself might cease as reality crystallizes into eternal stasis. The second law of thermodynamics, which states that entropy always increases, would face an impossible paradox at light speed. Entropy measures disorder, and in a closed system it can only stay the same or increase. But a light-speed object with infinite energy concentrated in zero thickness would have undefined entropy. The universe might respond by maximizing entropy instantly everywhere, jumping directly to heat death, that final state trillions of years in our future where no more work can be done, no more stars can shine, and no more life can exist. Consider what we've learned from studying neutron stars through telescopes like NICER aboard the International Space Station. These city-sized remnants of supernovae pack more mass than our Sun into spheres just 20 kilometers across. Their gravity is so intense that a teaspoon of neutron star material would weigh about 5 billion tons on Earth. Yet even these extreme objects obey the cosmic speed limit. Pulsars, rapidly spinning neutron stars, can rotate hundreds of times per second, but their surfaces never exceed light speed. An object actually reaching light speed would make neutron stars look gentle by comparison. The strong nuclear force, which binds quarks into protons and neutrons, exhibits a peculiar property called asymptotic freedom. At extremely high energies, quarks interact more weakly, while at low energies, they're confined. The infinite energies of light-speed travel would push beyond asymptotic freedom into uncharted territory. Quarks might become completely free, dissolving all atomic nuclei instantly, or the strong force might respond unpredictably, perhaps becoming repulsive and blowing apart every atom in existence. The weak nuclear force, responsible for radioactive decay and stellar fusion, would also behave unpredictably at infinite energies. The W and Z bosons that mediate this force have mass, unlike photons and gluons. At light speed, these force carriers would have infinite mass, making weak interactions impossible. Radioactive decay would cease. Stars would stop fusing hydrogen into helium. The processes that create heavy elements and power life would end instantly throughout the universe. Electromagnetic fields around a light-speed object would become infinite in strength. Maxwell's equations, which describe electricity and magnetism perfectly at normal energies, break down at these extremes. The magnetic field of a moving charge increases with velocity, approaching infinity at light speed. This infinite field would induce infinite currents in any conductor, creating more infinite magnetic fields in an endless feedback loop that could magnetize the entire universe instantly. The Chandrasekhar limit tells us white dwarf stars can't exceed about 1.4 solar masses without collapsing. The Tolman-Oppenheimer-Volkoff limit sets a similar boundary for neutron stars at around 2 to 3 solar masses. These limits exist because gravity eventually overwhelms all other forces. A light-speed object with infinite mass would exceed all possible limits simultaneously, potentially triggering every possible type of stellar collapse throughout the cosmos through gravitational resonance. Recent observations of kilonovae, explosions from merging neutron stars, have shown us how extreme events create heavy elements. The merger GW1 70817 detected by LIGO and observed electromagnetically, produced gold and platinum equivalent to several Earth masses. A light-speed event would involve infinitely more energy, potentially transmuting all matter into forms we can't predict. The periodic table might be rewritten with elements that can't exist under normal conditions. The Casimir effect demonstrates that quantum vacuum fluctuations have real, measurable consequences. Parallel conducting plates experience an attractive force because they exclude certain vacuum fluctuations between them. At light speed, length contraction would effectively create zero separation between all objects along the direction of travel. The Casimir force would become infinite everywhere, potentially crushing all matter into two-dimensional sheets or worse. Hawking radiation shows that even black holes eventually evaporate by emitting particles. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter. An infinite mass black hole created by light-speed travel would have zero temperature, emitting no Hawking radiation. It would be an eternal wound in space-time, never healing, always growing, eventually consuming everything. The cosmic web structure revealed by galaxy surveys like the Sloan Digital Sky Survey shows matter organized into filaments and voids. This structure formed through gravitational instability over billions of years. Light-speed travel would create gravitational shocks that propagate along these filaments at light speed, potentially causing the entire web to collapse instantly. The large-scale structure that took cosmic history to build would be erased in moments. Quantum tunneling allows particles to pass through barriers they classically shouldn't overcome. The probability decreases exponentially with barrier height and thickness, but a light-speed object with infinite energy could tunnel through any barrier with probability 1. This means it could spontaneously appear anywhere in the universe, potentially everywhere simultaneously. Locality itself, the principle that objects only directly affect their immediate surroundings, would break down completely. The Planck scale, where quantum gravity effects dominate, occurs at distances of 10 to the negative 35 meters and energies of 10 to the 19 GeV. Light-speed travel would involve energies infinitely beyond the Planck scale. We'd enter a regime where our concepts of space and time cease to have meaning. The universe might pixelate, smooth out, or transform in ways our physics can't describe or predict. Observations from the IceCube Neutrino Observatory in Antarctica have detected high-energy neutrinos from distant cosmic events. These ghostly particles barely interact with matter, passing through entire planets unimpeded. At light speed, even neutrinos would carry infinite energy. A single neutrino collision could destroy a planet. The protective transparency of matter to neutrinos would become a cosmic vulnerability with no possible shielding against destruction. The arrow of time, that fundamental asymmetry that distinguishes past from future, emerges from thermodynamics and quantum decoherence. At light speed, with time dilation becoming infinite, there would be no arrow of time for the traveler. But worse, the infinite energy densities could reverse time's arrow locally or globally. Cause and effect might run backward in expanding bubbles, creating regions where entropy decreases, dead stars reignite, and broken objects spontaneously repair themselves until these regions collide with normal space-time in catastrophic paradoxes. CERN's experiments with heavy ion collisions have created quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. These collisions reach temperatures of 4 trillion degrees Celsius, 250,000 times hotter than the Sun's core. Yet this pales compared to light-speed energies. We'd create conditions that never existed even during cosmic birth, potentially triggering new Big Bangs within our existing universe, each expanding and overwriting reality with different physical laws. The fine structure constant, approximately 1/137, determines the strength of electromagnetic interactions. It appears in equations throughout physics, and its precise value seems necessary for atoms to exist. Infinite electromagnetic fields from light-speed travel could shift this constant. Even tiny changes would destabilize atoms. Electrons would spiral into nuclei or escape entirely. Chemistry would cease, life would be impossible. The universe would become a soup of disconnected particles. Cosmic rays have taught us about particle physics at extreme energies. The Pierre Auger Observatory in Argentina detects the highest energy particles reaching Earth. But these are individual protons or nuclei. A macroscopic object at light speed would be like focusing all cosmic rays that have ever hit Earth into a single point. The resulting particle cascades would convert matter into exotic forms, strange quarks, magnetic monopoles, supersymmetric particles, transforming the familiar universe into something alien and hostile. The gauge symmetries underlying fundamental forces would shatter at infinite energies. Electromagnetism and the weak force unify at high energies into the electro-weak force. At even higher energies, the strong force joins them. Light-speed travel might force all forces to unify instantly, but in an uncontrolled way. The distinct forces we rely on would merge into a single superforce with properties we can't predict, potentially making stable matter impossible. Dark matter halos, invisible structures holding galaxies together, have been mapped through gravitational lensing by telescopes like Hubble and the VLT. These halos respond only to gravity under normal conditions. But infinite gravitational fields from light-speed travel might trigger new interactions. Dark matter could suddenly couple to ordinary matter, releasing enormous energy as 2/3 of the universe's matter content suddenly becomes reactive. Galaxies would explode from within as their dark matter ignites. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. A light-speed object would be observed infinitely often by every particle it passes, potentially freezing the entire universe's quantum evolution. Radioactive atoms would stop decaying, chemical reactions would halt, photosynthesis would cease. Life processes, depending on quantum transitions, would freeze. The universe would become a static museum, preserved but dead. Gravitational lensing has revealed how mass bends light paths. The Hubble Space Telescope has captured Einstein rings, perfect circles of light from distant galaxies bent around massive foreground objects. A light-speed traveler with infinite mass would bend light infinitely, creating not just lensing but trapping all light that passes nearby. The universe would develop dark zones where light cannot escape, expanding regions of absolute darkness punctuated by infinitely bright caustics where light concentrates. The bootstrap paradox illustrates why faster-than-light travel threatens causality. Information could loop through time with no origin. Now imagine this with infinite energy at exactly light speed. Information wouldn't just loop, it would multiply infinitely. Every quantum of data spawning countless copies across spacetime. The universe's information content would diverge to infinity instantly, potentially crashing reality like an overloaded computer. Plasma physics in tokamak fusion reactors shows how charged particles behave in extreme conditions. The ITER project aims to confine plasma at 100 million degrees Celsius. At light speed, every atom would be ionized into plasma with infinite temperature. This wouldn't be confined to the traveler. Infinite electromagnetic fields would ionize all matter throughout the universe instantly. Stars, planets, and life would dissolve into an infinite temperature plasma filling all space. The strong CP problem in physics asks why the strong force seems to preserve certain symmetries. The proposed solution involves axions, hypothetical particles that might compose dark matter. Light-speed travel's infinite energies could spontaneously create or destroy axions throughout space, potentially solving or worsening the strong CP problem in ways that reshape fundamental physics. The universe's symmetries might break or impose themselves absolutely, either way ending physics as we know it. Observations of the early universe through the cosmic microwave background show tiny temperature fluctuations, about 1 part in 100,000, that seeded all cosmic structure. These delicate perturbations grew over billions of years into galaxies and clusters. Light-speed travel would create infinite perturbations, overwriting this careful pattern instantly. The universe's structure would be erased and replaced with infinite chaos or infinite uniformity, either way ending the complexity that allows stars, planets, and life. The quantum Hall effect reveals how matter behaves in extreme magnetic fields, electrons forming compressible fluids with quantized conductance. The infinite magnetic fields around light-speed objects would force all matter into exotic quantum Hall states. Ordinary materials would become superconductors, insulators, or stranger phases. Electronic technology would fail. Biological processes depending on electron transport would cease. Matter would be locked into quantum states incompatible with life. String theory suggests reality consists of vibrating strings in higher dimensions. Different vibrational modes create different particles. Infinite energies from light-speed travel would excite all possible vibrational modes simultaneously. Every possible particle would be created in infinite quantities: quarks, leptons, bosons, and exotic particles we haven't imagined. The vacuum would become an infinitely dense soup of all possible particles, essentially a new Big Bang, but without the organizing principles that made our universe habitable. The cosmic censorship principle faces its ultimate test with light-speed travel. When the LIGO and Virgo detectors observe black hole mergers, they're watching nature hide singularities behind event horizons. But a light-speed object would be a naked singularity exposed to the universe, infinite density and curvature without the decency of an event horizon. The universe's response might be to emergency create horizons everywhere, turning all of space into the inside of a black hole where different physics applies and escape becomes impossible. Neutron star observations by NASA have revealed their equations of state, how matter behaves at nuclear densities. Even in these extreme objects, particles maintain their identities as neutrons, with some exotic quark matter possibly at the cores. Light-speed travel would push far beyond nuclear densities into realms where the concept of particles breaks down entirely. Matter wouldn't just be compressed, it would lose the quantum numbers that distinguish one particle from another, creating an undifferentiated cosmic soup. The ADS-CFT correspondence, one of string theory's greatest insights, suggests our universe might be holographically dual to a lower dimensional boundary. This duality requires precise mathematical relationships between bulk physics and boundary physics. Infinite energies from light-speed travel would break this correspondence, potentially severing our three-dimensional reality from its holographic encoding. We might literally fall out of existence as the mathematical framework supporting reality collapses. Pulsar timing arrays like nanogravs search for gravitational waves by monitoring millisecond pulsars with extraordinary precision. These cosmic clocks are so regular that we can detect timing variations of nanoseconds over years. A light-speed event would send gravitational tsunamis that don't just perturb pulsar timing, they would shred the pulsars themselves. Every precision clock in the universe would be destroyed simultaneously, ending our ability to measure time on cosmic scales. The false vacuum hypothesis gained support when the Higgs boson's mass was measured at 125 GeV. This value places our universe near the edge of metastability. The infinite energy densities around light-speed travel wouldn't just risk triggering false vacuum decay, they would guarantee it. Multiple decay bubbles would nucleate simultaneously, expanding at light speed with different random vacuum values. Where these bubbles collide, the energy release would exceed the Big Bang itself. Loop quantum gravity attempts to quantize spacetime itself, suggesting space consists of discrete loops at the Planck scale. Light-speed travel would pump infinite energy into these loops, potentially unraveling the quantum geometry of space. Imagine spacetime as a knitted fabric. Pulling one thread infinitely hard doesn't just stretch it, but unravels the entire weave. Reality might literally come apart at the seams, leaving nothing, not even vacuum. The delayed choice quantum eraser experiments show that future measurements can seemingly affect past quantum states. A light-speed object existing everywhere along its trajectory simultaneously would perform infinite measurements on every quantum system it passes. This wouldn't just collapse wave functions, it would create temporal paradoxes where past states depend on future measurements in circular loops. Causality wouldn't just be violated, it would tie itself in knots that make consistent history impossible. Observations of galaxy rotation curves led to dark matter's discovery. The Gaia spacecraft has mapped stellar motions in our galaxy with unprecedented precision, confirming dark matter's gravitational effects. Light-speed travel would create infinite gravitational fields that force dark matter to reveal itself catastrophically. If dark matter consists of WIMPs, they might annihilate en masse. If it's axions, they might convert to photons. Either way, 2/3 of the universe's mass suddenly converting to energy would create a cosmic bomb. The quantum chromodynamic scale, where the strong force becomes strong, occurs around 200 MeV. Above this energy, quarks are nearly free. Below it, they're confined. Infinite energies would push so far beyond this scale that our understanding breaks down completely. The strong force might become repulsive, exploding every nucleus, or it might become infinitely attractive, crushing all matter to quark soup. The color force that paints reality might run wild, creating new forms of matter hostile to current existence. Baryogenesis, why matter dominates over antimatter, remains one of physics' great mysteries. The Sakharov conditions require baryon number violation, CP violation, and non-equilibrium conditions. Light-speed travel would create extreme non-equilibrium with infinite energies, potentially triggering new baryogenesis. Matter and antimatter might be created in equal amounts throughout space, leading to universal annihilation as every particle finds its antiparticle. The universe would become pure energy with no matter remaining. The Xenon and Lux experiments search for dark matter through incredibly sensitive detectors shielded from cosmic rays. They've found nothing yet, placing strict limits on dark matter interactions. Light-speed travel might force dark matter to interact strongly, turning every dark matter particle into a cosmic ray. The invisible universe would suddenly become violently visible, with dark matter annihilations lighting up space like a universal firework display before everything burns out. Magnetic monopoles, hypothetical particles with single magnetic poles, are predicted by many theories beyond the Standard Model. None have been found despite decades of searches. The infinite magnetic fields around light-speed objects might spontaneously create monopole-antimonopole pairs throughout space. These would annihilate violently, but in the process, they'd scramble magnetic fields everywhere. Compasses would spin wildly, dynamos would fail, planets might lose their protective magnetic fields, exposing all life to deadly radiation. The information paradox extends beyond black holes to any extreme physics scenario. Information should be conserved, but where does it go when matter is crushed to infinite density or heated to infinite temperature? Light-speed travel would create infinite information density along the traveler's path. The universe might respond by creating infinite entropy to accommodate this information, instantly jumping to maximum disorder. All structure, all complexity, all life would dissolve into random noise. The cosmic neutrino background, relic neutrinos from 1 second after the Big Bang, fills space with about 300 neutrinos per cubic centimeter. These ancient particles barely interact with matter, but at light speed, even neutrinos become deadly projectiles. Each collision would release infinite energy, turning the gentlest particles in the universe into agents of destruction. The cosmic neutrino background would become a universal death field, annihilating any matter it touches. MAGIC and HESS ground-based gamma-ray telescopes detect the highest energy photons reaching Earth from cosmic accelerators. These photons carry tremendous energy but still obey the cosmic speed limit. A light-speed object would blue-shift all radiation to infinite frequencies. Every photon in the universe, from radio waves to gamma rays, would become infinitely energetic from the traveler's perspective. The cosmic microwave background at 2.7 Kelvin would become a wall of infinite energy gamma rays. The Heisenberg uncertainty principle sets fundamental limits on knowledge. We can't simultaneously know position and momentum perfectly. At light speed with infinite momentum, position becomes infinitely uncertain. The traveler wouldn't just be somewhere along their path, they'd be everywhere in the universe simultaneously. This infinite delocalization would entangle them with every particle in existence, creating a universal quantum measurement that collapses all wave functions into a single, frozen state. Superconductivity demonstrates quantum mechanics on macroscopic scales. Below critical temperatures, materials conduct electricity without resistance through Cooper pairs of electrons. The infinite electromagnetic fields from light-speed travel would break all Cooper pairs instantly, destroying superconductivity throughout the universe. But worse, they might force all matter into exotic superconducting states, creating universal quantum entanglement that locks the universe into a single macroscopic quantum state. The Meissner effect expels magnetic fields from superconductors, creating perfect diamagnetism. Infinite magnetic fields from light-speed objects would trigger infinite Meissner effects in any superconducting matter. The resulting forces would be unlimited, potentially tearing apart any organized matter. Planets with metallic cores might explode, stars with degenerate matter might shatter. The universe's magnetic architecture would collapse into chaos. Cherenkov radiation occurs when particles exceed light speed in a medium. The ice cube detector uses Antarctic ice to spot the blue glow from high-energy neutrinos. In vacuum, nothing can exceed light speed to create Cherenkov radiation. But light speed travel might change vacuum itself into a medium with different properties. The entire universe could glow with Cherenkov radiation as the nature of empty space transforms, bathing everything in deadly blue light. The quantum vacuum isn't empty but seethes with virtual particles. The Schwinger limit marks where electric fields become strong enough to create real particles from vacuum. Light-speed travel would exceed this limit infinitely, turning all of space into a particle factory. Electron-positron pairs would materialize everywhere, immediately annihilating in flashes of gamma rays. The vacuum would boil with particle creation and destruction, turning empty space into a dense plasma. Penrose diagrams map the entire spacetime of black holes, showing how infinity gets compressed into finite diagrams. A light-speed object would require impossible Penrose diagrams with actual infinities that can't be mapped. The mathematical tools physicists use to understand spacetime would break down. We'd face not just physical catastrophe, but conceptual catastrophe, the inability to even describe what's happening mathematically. The Kerr metric describes rotating black holes where rotation creates an ergosphere, a region where spacetime itself rotates. Objects in the ergosphere must rotate with the black hole. A light-speed object would create an infinite ergosphere, forcing the entire universe to rotate. But rotate around what? The paradox might tear space-time apart as every point tries to rotate around every other point simultaneously. Gravitational time dilation, confirmed by GPS satellites and atomic clocks, shows time runs slower in stronger gravitational fields. Infinite gravity from light-speed travel would create infinite time dilation. Time would stop completely near the traveler. But this creates paradoxes. How can the traveler move if time is stopped? The universe might respond by fracturing time itself, creating regions where time runs backward, sideways, or not at all. The Unruh effect predicts that accelerating observers see blackbody radiation in vacuum. The temperature is proportional to acceleration. Greater acceleration means hotter radiation. Infinite acceleration to reach light speed instantly would create infinite temperature Unruh radiation. The traveler would see empty space as hot as possible, Planck temperature where physics breaks down. This radiation would be real from their perspective, incinerating them and potentially heating the actual vacuum. Cosmic inflation solved several Big Bang puzzles by proposing rapid exponential expansion. But inflation was controlled, driven by a special field that turned off gracefully. Light-speed travel might trigger uncontrolled inflation as infinite energies destabilize whatever keeps space from expanding. Different regions might inflate at different rates, tearing the universe into causally disconnected bubbles, each developing different physics most hostile to matter as we know it. The electroweak phase transition occurred when the universe cooled below a critical temperature, splitting electromagnetism from the weak force. Infinite energies could reverse this transition, reunifying the forces violently. Atoms would become impossible as electrons and quarks interact through the unified electroweak force. All matter would dissolve into a quark-lepton soup like the universe microseconds after the Big Bang, but without the expansion and cooling that allowed matter to form. Quantum field renormalization saves particle physics from infinities by careful mathematical cancellation. But physical infinities from light-speed travel can't be renormalized away. They're real, not mathematical artifacts. The techniques physicists use to make sense of quantum field theory would fail catastrophically. We'd face naked infinities that make calculations impossible and predictions meaningless. Physics itself would become undefined. The hierarchy problem asks why gravity is so much weaker than other forces, 10 to the 39th times weaker than electromagnetism. Some theories propose extra dimensions where gravity spreads while other forces remain confined to our three-dimensional brain. Light-speed travel might rip open these extra dimensions, suddenly equalizing force strengths. Gravity becoming as strong as electromagnetism would collapse every atom instantly. Electrons would spiral into nuclei. Chemistry would end. Matter would compress into universe-wide black hole formation. Observations from the Dark Energy Survey have mapped millions of galaxies, revealing the universe's large-scale structure. This cosmic web formed through tiny density fluctuations amplified by gravity over billions of years. Infinite gravitational waves from light-speed travel would erase these patterns instantly, like shaking an etch-a sketch. The delicate architecture that took cosmic history to build would vanish, replaced by either perfect uniformity or infinite chaos, both equally hostile to structure formation. The lithium problem, why Big Bang nucleosynthesis predictions don't match observed lithium abundances, hints at unknown physics in the early universe. Light-speed travel might trigger similar nucleosynthesis throughout space as infinite energies recreate primordial conditions. But without the precise conditions of the original Big Bang, the results would be catastrophic. Protons and neutrons might fuse randomly, creating unstable isotopes that immediately decay, bathing the universe in deadly radiation. Quantum decoherence explains how quantum systems become classical through environmental interaction. It's why we don't see macroscopic superpositions. Schrödinger's cat is either alive or dead, not both. Light-speed travel would cause infinite decoherence as the traveler interacts with every particle simultaneously. But paradoxically, it might also prevent decoherence by freezing quantum evolution. The universe might get stuck between quantum and classical, unable to be either. The Mini-Booney experiment at Fermilab has hinted at possible sterile neutrinos that don't interact through any force except gravity. If they exist, infinite gravitational fields might force them to interact, revealing a hidden neutrino sector. Trillions of invisible particles might suddenly become visible, interacting with matter in unpredictable ways. The ghostly neutrino background could become a tangible wall of particles, blocking light and disrupting stellar fusion. Axion searches like ADMX look for hypothetical dark matter particles that could solve the strong CP problem. These experiments use powerful magnetic fields to convert axions to photons. Infinite magnetic fields from light-speed travel would convert all axions instantly, flooding space with photons. If axions compose dark matter, 2/3 of the universe's mass would suddenly become radiation. Galaxies would explode from within as their dark matter, halos, convert to pure energy. The spin statistics theorem connects particle spin to quantum statistics. Fermions have half-integer spin, bosons have integer spin. This fundamental rule determines matter's structure. Infinite rotational effects from light-speed travel might scramble spin assignments. Fermions might become bosons, allowing all electrons to occupy the same state. Atoms would collapse. Matter would condense into bizarre bosonic states. The distinction between matter and force carriers would vanish. Plasma wake-field acceleration, studied at SLAC and other facilities, achieves incredible particle accelerations over short distances. But these controlled experiments pale before light-speed scenarios. The infinite wake field from a light-speed object would accelerate all nearby particles to extreme energies, creating cascading particle showers that propagate outward. Space itself would become a universal particle accelerator, converting all matter to high-energy radiation. The cosmic distance ladder, how we measure the universe's scale, depends on standard candles like type Ia supernovae. These stellar explosions have consistent brightness because they occur when white dwarfs reach the Chandrasekhar limit. Infinite gravitational fields would trigger all white dwarfs simultaneously, regardless of mass. Every potential type Ia would explode at once, not only destroying planetary systems, but erasing our ability to measure cosmic distances. Bell's theorem proves quantum mechanics is non-local. Entangled particles coordinate instantly, regardless of distance. Light-speed travel would create infinite entanglement, as the traveler exists everywhere, simultaneously. This wouldn't violate Bell's theorem, but fulfill it absolutely. Every particle would be maximally entangled with every other particle. The universe would become a single quantum system with no independent parts, no possible measurements, no classical reality. The blackbody radiation spectrum, explained by Planck and launching quantum mechanics, describes thermal radiation from objects. The cosmic microwave background is an almost perfect blackbody at 2.725 Kelvin. Infinite blue shifting from light-speed travel would push this temperature to infinity. The universe would be filled with Planck temperature radiation, the hottest possible. Matter, energy, even space-time geometry would melt in this infinite thermal bath. Topological defects like cosmic strings or domain walls might exist from phase transitions in the early universe. These structures would respond catastrophically to infinite energies. Cosmic strings might snap, releasing energy comparable to their entire mass. Domain walls might collide and annihilate. Magnetic monopoles might be created or destroyed en masse. The universe's hidden topology would unravel, potentially changing the fundamental structure of space. The Sunyaev-Zeldovich effect shows how cosmic microwave background photons gain energy passing through galaxy clusters. Light-speed travel would create an infinite version of this effect. Every photon in the universe would gain infinite energy passing near the traveler. The CMB wouldn't just be blue-shifted from the traveler's perspective, it would be physically heated to infinite temperature everywhere, turning the universe's baby picture into a universal crematorium. Neutron decay, normally taking about 15 minutes for free neutrons, maintains the universe's proton-neutron balance. Infinite time dilation would freeze neutron decay from the traveler's perspective, while accelerating it from outside perspectives. This temporal paradox might cause all free neutrons to simultaneously decay or become stable, disrupting nucleosynthesis in stars. The careful balance enabling stellar fusion would shatter, potentially extinguishing every star instantly. As we reach the conclusion of this cosmic horror story, let's confront the ultimate paradox. The very attempt to reach light speed might prevent its own success through universe-ending feedback loops. The moment acceleration begins toward light speed, the increasing energy density would start warping spacetime. This warping would make further acceleration harder, requiring more energy, creating more warping. The universe might defend itself through an exponentially growing barrier that becomes infinite before light speed is reached, but if somehow breached, would release that infinite stored energy catastrophically. The Large Hadron Collider has taught us that high-energy physics often produces unexpected results. When protons collide at 99.99999% light speed, they create not just predicted particles, but sometimes hints of new physics. The infinitely higher energies of true light-speed travel wouldn't give hints, they'd rewrite the rulebook entirely. Every assumption physicists make, every equation we trust, every constant we measure would become obsolete in an instant. Consider what this means for the anthropic principle. We exist in a universe where physical constants allow atoms, stars, and life. These constants seem fine-tuned, change any by tiny amounts, and complexity becomes impossible. Light-speed travel would effectively randomize these constants through infinite energy interactions. The probability of them settling into life-permitting values again is essentially zero. We wouldn't just be destroying our universe, we'd be destroying any possibility of a habitable universe. The cosmic perspective makes this even more profound. When astronomers like Edwin Hubble discovered universal expansion, when physicists like Einstein revealed spacetime's nature, they were uncovering safety mechanisms. The speed of light isn't a limitation, it's a protection. The universe has built-in safeguards against its own destruction, and the cosmic speed limit might be the ultimate firewall protecting existence itself. SETI's searches for extraterrestrial intelligence have found only silence. The Fermi paradox asks why, given the galaxy's age and size, we see no evidence of advanced civilizations. Perhaps every sufficiently advanced species discovers what we're discussing today, that pushing against the universe's fundamental limits risks everything. Maybe the great filter isn't war or disease, but the temptation to break the light barrier, and civilizations either accept the limit or cease to exist. The multiverse hypothesis suggests our universe is one of possibly infinite others, each with different physical laws. If light-speed travel could destroy a universe, it might also affect neighboring universes in the multiverse. The catastrophe might not be locally contained but could cascade through multiple realities, erasing entire branches of existence. We might not just be risking our cosmos, but all possible cosmos connected to ours. Quantum mechanics teaches us that observation affects reality. The delayed choice quantum eraser shows that future measurements can influence past states. A light-speed traveler existing everywhere on their path simultaneously would be performing infinite observations on every quantum system. This wouldn't just collapse wave functions, it would lock the universe into a single, observed state forever. The quantum uncertainty that enables change, evolution, and life would vanish. The simulation hypothesis offers a chilling possibility. If our universe is simulated, light speed might represent the simulation's maximum processing rate. Attempting to exceed it would be like trying to overflow a computer's memory or divide by zero. The simulation might crash, freeze, or reset. We wouldn't experience destruction, we'd simply cease, deleted like a corrupted file, with no warning or trace. But perhaps the most terrifying possibility is that we're wrong about the catastrophe's nature. We've discussed physical destruction, but what if the real danger is informational? The universe might be a vast quantum computer processing information. Light-speed travel could corrupt this processing, not destroying matter but scrambling the information that defines it. Particles might forget what they are, forces might forget how to act. The universe wouldn't explode, it would experience cosmic amnesia, forgetting how to be a universe. Recent discoveries keep reinforcing these limits. The James Webb Space Telescope shows us galaxies from the universe's youth, their light crawling toward us at exactly light speed for billions of years. Gravitational wave detectors confirm that even space-time ripples respect the cosmic speed limit. Every observation, every experiment, every theoretical breakthrough reinforces the same message. The speed of light is absolute, and attempting to break it isn't just impossible, it's potentially catastrophic. The beauty is that understanding these limits doesn't diminish us, it elevates us. We're arrangements of atoms that have figured out why we can't travel at light speed. We've discovered the universe's safety mechanisms, understood the price of existence, glimpsed the catastrophes that physics prevents. This knowledge itself is a form of transcendence. We might be forever slower than light, but our understanding can encompass concepts that light itself cannot reach. So why can't we travel at light speed? Because the universe is protecting itself and us from annihilation. Every physical law, every constant, every force conspires to prevent this ultimate catastrophe. The cosmic speed limit isn't a cage, it's a foundation that allows atoms to be stable, stars to shine, planets to orbit, and life to evolve. Breaking it wouldn't free us, it would unravel everything. The next time you see stars twinkling in the night sky, remember that their light traveled for years to reach you, respecting the cosmic speed limit every kilometer of the journey. That faithful obedience to physical law is what allows those stars to exist, allows you to exist, allows the universe to be a cosmos rather than chaos. The speed of light isn't just a number, it's the universe's promise to remain comprehensible, stable, and real. This is perhaps the deepest lesson. The universe's restrictions are also its gifts. By preventing light-speed travel, physics protects causality, maintains the arrow of time, preserves information, and ensures that existence remains possible. We might dream of breaking free from these limits, but we should be grateful for them. They're not preventing our ultimate adventure, they're enabling our existence in the first place. Thank you for joining me on this journey through physics' ultimate catastrophe scenario. If this exploration has given you a new appreciation for the universe's hidden safety mechanisms, please share it with someone who dreams of breaking the rules. Subscribe to continue exploring the boundaries between possible and impossible, between knowledge and catastrophe. And remember, we might be forever bound by the speed of light, but that boundary is what makes us and everything we love possible. Until next time, Keep looking up at those speed-limited stars and be grateful that the universe knows how to protect itself from our wildest ambitions. If you are still watching, make sure to subscribe to the channel and give a thumbs up. Your support is my biggest fuel to keep motivated. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never reach light speed. In this video, we dive deep into the real science behind the cosmic speed limit and reveal why traveling at the speed of light is fundamentally impossible, not just for humans. See you there.